Sar Amar, and I'm here to share with you the story of how I found and exploited a really hardcore vulnerability in WSL. I gave this talk at the Blue Hat IL, which was 2 weeks ago. And it's basically going to be the same thing with some additional info because I have a little bit more time now. So let's start. A little bit about myself. I am a security researcher. My whole point in life is about reversing and exploiting vulnerabilities. I'm also addicted to SCTFs. I'm on past 10 CTF team, which you probably heard of us by now. So today, we're going to see a very little bit of WSL, see the vulnerability, understand it, analyze it, and of course, focus all our effort and energy on the fun and interesting part, which is, of course, the exploitation phase. We have a lot of work to do here and a quite short period of time to do that, so please welcome WSL. So WSL is the Windows subsystem for Linux. It was introduced in the kernel of Windows 10. Basically, it lets you execute a Linux binary natively on your Windows host. It implements all of the Linux syscall, file system, elf parsing, etc. And the interesting point here is that all of that functionality is actually implemented in one new massive driver called lxcoresys. Some of that, the most actually is just like wrapping existing logics from the anti-kernel, but there were some parts which was re-implemented from scratch, like for the Linux pipes, for example. I don't want to talk about something which is highly documented and very, very common knowledge. And like any new tech for Microsoft, there is a great talk of Alex and Esco describing it perfectly. So please, if you're into it, check out the talk of Alex from Leket in 2016. I'm sure you will find it quite interesting. Okay, so are you guys trying to tell me that there is a whole new driver inside the Windows kernel which does a lot of parsing and implements a lot of non-trivial implementation, and it passes data that can be controlled from low-privileged user from user space, and you expect me not to reverse it? So no, this is not how it works, okay? Like, if Microsoft does something like this, we stop to live, we sit down, and we reverse this thing like full power, okay? Because this is what life is about. If I don't do that, I don't see quite like reason to wake up in the morning. So this is what we need to do. So it's actually a very, very funny story. I sat down with a great friend of mine, Tomer, and we sat down. It was a very, very late hour, and it drank a lot of whiskey. And we talked about why we never talk in conferences, because we have a lot of cool stuff to talk about, but we never do. And then we were like, hey, wait, there is all of this WSL thing. We're pretty sure that we can break this thing down. So we said bye. I went home, and after all of that whiskey, I fall asleep. But when I wake up, I start to reverse lxcoresys. And then I get into a very, very odd behavior in a function that tries to read an array of strings from user space. The function name is lxputil read user string set, and it does exactly what its name suggests, okay? It fetches the user space, read an array of strings, and copy it to a buffer allocated on the page pool, okay? Pretty simple. Now, the function tries to create this buffer, okay? It allocates it on the page pool, and it writes into it all of the strings from user space with some additional metadata which describe those strings. Now, the metadata contains headers, one header for each string, and each header contains both the length and the length -1 of the string it tries to represents. I have no idea why Microsoft thought that it's necessary to hold both of them, but apparently they did. And of course, a pointer, which points to the beginning of the relevant string. Now, there is basically like a loop, okay, which writes string header, and they write the metadata to the beginning of the chunk, and then they write the strings, okay? Now, I want you to note two critical points in this function. The first one is that the function double fetch, okay? Because the function needs to know the amount of string and their total length in order to allocate the buffer. So it has to fetch to user space in order to retrieve that info, allocate the buffer, and only then fetch again in order to copy. So the function double fetch, which, like mem says, okay, you know, it's fine. And the second point is that from the memory management perspective, this is one allocation on the page pool, okay? This is one allocation, and the size of the allocation is, of course, the total string length plus the amount of strings times the size of the header. Now, whenever you do an allocation of size, which is a result of an arithmetic expression, you need to be very, very careful, of course, for integers overflow and underflow. So apparently, Microsoft does aware of that, and they do check that the total string length won't overflow. They do check that the addition won't overflow, so nothing can basically like do integer overflow or to wrap around here. But they missed the multiplication. And since the multiplication is done in 32-bit calculation, it's highly easy to achieve this overflow, okay? So all you need to do is just to set up a very large array at user space with 32-bit divided by 18 hex entries, which ends up with AAA, okay? And trigger that flow on that array. And then this arithmetic, which calculates the size of the chunk on the page pool, will like wrap around, okay? And this is very, very interesting situation. Now, how is that integer overflow will affect the chunk that we just saw? So, as I told you, there is the while loop, okay, which writes all the strings and the headers come at the beginning of the chunk, but now, since the consider space for the metadata is basically 0, because this value just like wrap around, so both the strings and the metadata will begin from the beginning. Now, it's not quite interesting because they write string header, as I told you, so the headers will override all of the string data. And it's fine because we can't corrupt with the strings anyway, right? Because you start to write the strings to a position that you know for sure that you have total string length allocated bytes, because they do check for integer overflows on the addition. So the strings can corrupt anyway, but you will corrupt with the headers, and you will corrupt a lot, because you consider a very, very small space for the headers because of the integer overflow, but you have a bunch of them. You have at least AAA of them. So the headers will corrupt a lot on the page pool. Okay, cool. Now, what is the first question that we need to ask when we have such a vulnerability in hand? How can we trigger it? What is the flow to that vulnerability, right? Because if I don't have a flow, if I don't write a POC, I don't really hold something interesting, okay? I all the time say that if you think that you have a vulnerability, you need to write a POC, okay? You think you have the corruption, write a POC to segfault. You think you have information in disclosure, leak me some pointers or sensitive data. You need to write something, okay? And actually here, it's very, very simple, right? Because all that I need is some Linux syscall, which read an array of strings from user space. And like any syscall here's kid can know, it's the execv syscall. Execv does exactly that, okay? And you can see how simple and trivial this flow is, okay? So all we need to do is just to set up a very, very large array at user space and call execv on that array, okay? And basically, it will do the trick. Of course, we need to see the POC, so let's do it. I hope that you can see that. And if no, yeah, okay. So here I have my Windows 10 machine, okay? So we can just execute bash. Now, so this is my VM, okay? And this is the kernel debug which debugs it. So if there is a crash, the debugger will catch it. So let's go to +10 because we need to +10. And execute the POC. Now, the POC just looks like this, okay? I just need to allocate a very, very large array at user space, okay? And call execv on that array. It's very simple, very trivial, okay? There is no dark magic here, it's only bytes, okay? So let's execute the POC. Now the kernel starts to fetch all the strings from user space, and you can see on the debugger that we have a bug check on a 50x, okay? 50x is page fault in on-page area. This is the worst number a human being can see, and I am just about to explain why. But of course, we can do go in the debugger, and then you all can see that we crashed the kernel. So, cool. Fantastic. We'll get back to you later. Okay. The POC is actually really, really simple. It can fit like in one tweet, okay? I really hope that you saw that. I tweeted it before the Blue Hat. It was very nice, did a lot of noise, and now we can finally let the fun begin. Okay, now is actually why I built this talk from the first place. So bit of words of motivation, okay? And this is from a blog post from the Project Zero. It was written by Chris Evans from 2014. It's from the time that he like rocked there. It's actually my view of life, okay? I think I am reversing now for over 10 years, I think. I think that is the best thing that a man can do. I learn a lot while I do that, and I see IDA 20 hours a day, okay? But there is so much opportunities to learn new stuff, a new mechanism, while you write a full exploit. And that's why I think that people need to write exploit for all the vulnerabilities that they found, because even if you think that you understand all the flow and every bit of the vulnerability that you found, when you write the exploit, you see that you didn't. And there is much, much more that you can learn, okay? So we are about now to achieve arbitrary code execution in ring 0, and no, I don't just go to patch the token of the process with arbitrary write like primitive, okay? I actually going to execute arbitrary code in ring 0, and it's highly important. So the first question that we need to ask is what the primitives that the vulnerability gives us, right? Like what I can do using that vulnerability. So of course we have a pool overflow. We can corrupt bytes on the page pool. That's easy. But there is a bunch of questions that need to be asked. Again, like can we control the length of the corruption? And can we control the content of the corruption? Sadly, the both answers to this question is no, we can't. And this actually raises two massive issues, okay? The first massive problem here is that it's not just that I can control the length of the corruption, because if it was just that, it would have been easy. It's actually that I have a wild copy here, okay? And when I say wild copy, I mean that I have to write 4 gigabytes, okay? Because we corrupt with the headers, and the length of the headers is valued at just wrap around 32 bits, so it has to be at least 4 gigabytes. And I consider a very, very small space for the headers, right? So I write a massive data to a very, very small considered space. And when I do that, with a probability 1, I will reach to paged out area on the page pool, which for sure trigger page fault in on-page area, which is 50x, with the exact kbackcheck code you just saw in the POC. So this is a very, very bad state for 2 reasons. The first one is that this is a very bad panic, okay? A bad panic is a crash that doesn't indicate that I can do something good, okay? I want a crash on the reference of 4141 or on double free or Stefan linking violation, something that indicates that I can do something good. Page fault in on-page area is kind of lame, you know, I don't think that I can do really, really cool and intuitive stuff there. So I want to gain another panic, okay? I need to crash on something else. And for that, I will probably need to corrupt some structure and trigger the use of that, okay? And this is lead us to the second issue with that panic, okay? Even if you go to exploit that vulnerability and you find an interesting structure, shape it, corrupt it, and then try to use it, you won't get to use any corrupted structure because the wild copy always wins. Okay? The thread which copies the kernel won't stop, it won't rest until it will panic you, it crashes the system, and it happens before you get to use any corrupted structure. So the first thing that I need to do here is to stop the wild copy. And until I stop the wild copy, there is no point in doing anything because all of my work go to hell since the wild copy always wins. So this is the first massive problem. This is the first thing that I am about to solve in 5 minutes. And it's highly important to do that first. Now, let's assume just for fun, okay, that I give you as a Christmas present a really cool technique to stop the wild copy, okay? So this is on me. I will stop you the wild copy. You still have a problem because even if you find the perfect structure, which has pointers that you can read from, write to, and jump to, or it has length or something like that, you still corrupt with the headers. And the headers are just like len -1, len pointer, len -1, len pointer. So we can't control the content that you corrupt with. So we need to solve that. Now, you probably are sitting here and are like, hey, dude, you corrupt with pointer, which points to data that you can control. It's perfect. It's even bypassed the KSLR for you, okay? So no, this is extremely bad pointer. And the reason that this is a very, very bad pointer is because the size of the allocation have to be extremely huge because there is an integer overflow check on like that addition, okay? And I need to have at least a strings here. And when you free such a massive allocation on the page pool, those pages with extremely high probability will be paged out. And if I dereference that pointer to the string, I go back again to the issue of 50 hex backcheck page fault in on-page area. So I can't dereference that pointer, and I can't use that pointer to fetch structure or to do something interesting. Now, there will be a lot of people who try to reclaim those pages just like by spraying the kernel, okay? You can do that, but it's lame, okay? It's bad, because this will affect the reliability of the exploit, and I want my exploit to be extremely reliable, okay? The exploit code are, like actually, in my GitHub, you can execute it how many times you want. I execute it twice at the blue IL talk, and we will exploit it, we will execute here in front of you twice again. And if I want the exploit to be like extremely reliable, I need to avoid bad rings like that, okay? So I want the reference that pointer because I know I can find better primitives. Now, I want you to mark my words. I want the reference that pointer, okay? It's extremely, extremely important. So this is the second massive problem that we need to solve, that we can't control the content of the corruption. Okay. So as I told you, the first thing that I need to do is stop the wild copy, because if I want, there is no point in leaving, so let's stop the wild copy. There are a few options for that, right? The most trivial one is just to rely on a context switch. I can find some interesting structure, shape it, corrupt it, and then rely on a context switch. We transfer the execution from the thread which copies the kernel to another thread which will use that corrupted structure, and then I can execute code and stop the wild copy myself. Now, I can do that, but again, it's extremely unstable. And I want to avoid unstable tricks, so I refuse to do that. The second approach is just do what everyone did in the stage fright. A vulnerability, I assume you all know the stage fright, and if you don't, please do. It was extremely strong and powerful corruption in Android system. We had a wild copy there, but there I had a struct which had a virtual function, which by definition get called during the wild copy. So I can just shape that structure, corrupt it, and then by definition, while the wild copy executes, I jump to arbitrary rope that I built, and I execute code, and then I can stop the wild copy myself. This is the best that I can hope for, but sadly I don't have something like that here. So it's not relevant. And then we left with the third option, which is find a really cool and amazing trick to stop the wild copy and not do shit like this, sorry. So yeah, let's choose the third option. Okay, so do you recall that I told you that the function double fetch? Now, I can't count the time that people ask me, so I just gonna say it once. There isn't double fetch vulnerability here, okay? Really, there is not. They write to the stack the size of the allocation, and in the while loop, they write string header. They check all the time that they don't write out of bounds. So no, guys, seriously, stop asking me that. There isn't a double fetch vulnerability here. From that aspect, like Microsoft are fine, okay? But I don't need another vulnerability here. Actually, my problem is that I corrupt too much. I need to stop. I don't need another corruption. And I can use that to do a really, really cute and simple trick. I can call mmap with map shared at user space, and mmap for myself a very, very large area, okay? Now I can call fork, and one process at a user space will issue the exec syscall and trigger the vulnerability, okay? Now, the second process can just set a null pointer in the middle of the array, okay? And that will cause inconsistency like between the two fetches. Now, the function will detect this inconsistency, and it will stop, and it will return an error. But I don't care about that error, because that error stopped the wild copy for me, and at this point, I already corrupted the page pool. And this is fantastic. I just can control the exact amount of headers I corrupt with, which means that I can control the exact amount of bytes I corrupt it, up to multiplication of 18 hex, of course, which is the size of the header. So we stop the wild copy in a very elegant and like logic way, okay? And I can't hope for something like better than that. Now, if you recall, I told you that I can't see anymore the 50 hex K backcheck, the page fault in our page area. And if I see it one more time, I will probably shoot myself. So we need to use that technique of stopping the wild copy in order to see a good panic. Now, if I want to see a good panic, you exploit vulnerabilities, right? You need to find some structure, corrupt it, and then use it. But structure from their nature are very, very small. So I need to shape the page pool and locate small chunks after big ones. So let's start shaping. Now, again, I don't want to talk about something which is highly documented. Every kids know how to shape the page pool in the Windows kernel, but I give you the dots that you need to understand the shape that I will do in a few seconds. All the pools in the Windows kernel track free chunks, like using bitmaps. They use free list and executable, okay? It depends on the size of the chunk. But if you allocate chunk which exceeds the size of exactly one page, it goes to mi allocate pages in the CentOS, which means it uses bitmaps, and basically it's just the lower page available, okay? Now, those allocations are paged aligned, so if you allocate 7000, for example, the memory management will actually allocate 8 continuous pages. It will return to you the 7000 that you requested, and the remainder goes as a whole new free chunk to the corresponding free list, okay? Now, this is actually really cool because I can use that in order to create small chunks after big ones. The first thing that I need to do is to reach to a continuous area on the page pool. When I said continuous, I mean that I reach to a point when I know for sure that there is some size that I can allocate, which for sure I don't have a hole which can serve that size allocation before me. So I can just spray with C pages, and then I reach to continuous area on the page pool when I know for sure that there isn't a hole which can serve C pages allocation before, okay? Now I can start to create the workspace. The workspace is the name that I give to the area which I intend to drop the allocation of the vulnerable chunk, okay? I call that the workspace, so I start to allocate very, very large chunks because, as I told you, they have an integer overflow check on the addition, so I need to allocate a very, very large chunk here. And afterwards, I can allocate C pages minus some small size, which will create very small chunk right after my workspace. And it's great, because I can now spray with structure. I will drop one of the structure in that hole right after my workspace, and then I can free all of the large allocations. And when I do, I create a very large free chunk, and then I can issue the execv syscall and trigger the vulnerability. And then the vulnerable chunk drop right into the workspace, and when I do the corruption, I will corrupt the structure. And with using the really cool technique of stopping the wild copy, I will stop there. And that's it. Now, probably you ask yourself, why the hell I freed those small holes at the beginning? So this is because that I want to avoid the state which garbage from the kernel will allocated at the beginning of my free chunk, between this stage and that stage, okay? I don't want garbage from the kernel to get allocated on my workspace, so I create holes before my workspace, which can serve all of the garbage allocations that the kernel do all the time, okay? It's not the LFH here, okay? We have the networking, the file system, everything allocated on the same pool, so I need to create holes in order to save those allocations. Now, the primitive that I use to spray the kernel with the C page chunks is just the same get, okay? You know the semaphores in Linux, you have SM get, SM control, and etc. So I can just do that and gives a number of semaphore which will trigger the allocation of the C pages, but I bounded with the size there. And I need for my workspace to allocate a very, very large chunk. So I figure out that I can call fcontrol with fset pipe sz, and there I don't actually bounded with size, and I can allocate how many bytes that I want. So I use that. And if you combine everything together, you can see that I implement it all, okay? I choose the sham structure. It's really not important what struct I corrupted here, because I just want to get a good panic here, just to prove that both of the shaping and the stopping of the wild copy worked. And you can see that this is the kernel debugger which debugs the VM, okay? I put a trace on the vulnerable function. The size is 16000, which makes sense. If you go past that on the page pool, so we can see that we have BF10 allocation, which is great. It means that the shape worked because it's C pages, like minus the sham structure. And after that allocation, I have allocation of C0 with the LX tag, which is the LX core tag on the kernel allocations. And I do go in the WinDebug and I exit the shell. The exit of the shell triggers the freeing of all the sham structure that I sprayed with, and then we get 139K backcheck. We crash on a very, very good crash. 139 means safe unlinking violation. Okay, it's great, and it means that everything worked. And I finally stopped seeing that 50 hex K backcheck, and now I know for sure that I can do interesting stuff. Okay, so now we can start working. Fantastic. So now, after I know that I can corrupt good structure and use them, it's time to set up the course, okay? Like we need to decide where do we want to execute code from. Of course, the code will execute in the context of ring 0. Yeah, that's the basics. But we can execute it from user virtual address space or from the kernel virtual address space. And we can do both. Now, from the anniversary updates, all the PTEs in the kernel are randomized, and I need to find the PTE in order to go there to the 63-bit of the NX and deck it, because the page pool is not executable, because it's not the 18th century. And I don't want to do that, because most of the addresses of the PTEs are paged out, and then I go back to the page fault in non-page area. Shit. So yeah, I don't want to do that. And if I execute code from the user virtual address space, all I need to do is to disable SMAP, right? SMAP and SMAP, of course, are the mitigation in the processor which forbids the kernel to execute and access like user virtual addresses. SMAP is for access, is with A, and SMAP is for execute. So SMAP indicates that the kernel can't dereference user mode addresses. We don't have that in the Windows kernel at all, okay? By definition, all the Windows kernels don't have SMAP, but they do have SMAP. So I will need to do like a little rope, disable SMAP, and then jump to shellcode, which is fine, you know, it's like the way of living. It's fine. This is the time to put our hands together and cheer the teams for Microsoft of the Hyper-V and the VSM. None of that technique will work if you have VSM enable. I actually have an idea how I can escalate privileges of some arbitrary user mode process, even if we have VSM, but in this case, I won't execute arbitrary code in ring 0. I will tell you the idea afterwards, but now we don't have VSM, and we are going to exploit that vulnerability again and achieve arbitrary code execution. So let's do that. Now we can solve the second massive problem I just mentioned 15 minutes ago. I told you that we can control the content of the corruption, right? Because I corrupt with headers, and headers are like len -1, len pointer, len -1, len pointer. And I promised you that I won't dereference that pointer which points to paged out area. I'm going to keep my promise, and I won't dereference it, but I want you to note that the length of the string actually can be mapped as a valid user space address. Of course, I can set up a string which its length will be a valid kernel space address, because FFFF something is highly huge. I can do that. But I can set up a string with 2000 bytes. or C000 bytes, okay? And those values can be mmap as a valid user space addresses. And it's pretty cool, okay? And now it's the time to note that I can fake structure at user space and corrupt with pointers to those structures. And those pointers are just the length of the strings, and I can control them. And now it's the time to meet my new girlfriend. It's the sham object, the shared memory from Linux, okay? You all know it, sham get, sham control, sham et. And actually, it's pretty interesting because the Windows kernel track those objects in a linked list. At offset 0, they have the next pointer, and this just create a linked list on the page pool. And like when you call sham get, it allocates a new sham object, and you can do it how many times you want. So I can spray with that object, fantastic. And the sham et triggers a call to virtual function, which derives from that object. So if I corrupt that structure, I can gain arbitrary call, which is great. And here's come the really cool trick. I can corrupt the next field with the length of the string and break the linked list in kernel and reference it to user space. And then I can fake those sham structure as many as I like at user space, and I can write there everything I want, and I can write their pointers, and I can fake as many of levels of dereferences as I like. This is a really strong primitive. It's fucking crazy. I can fake structure, kernel structure at user space. And from that point, I own the whole system, okay? So let's just see that happen. I told you that I can call sham et right now. So if I just issue the sham et syscall, I can gain arbitrary call. I can call any address that I like. So if I just jump to a user space address now, I will need to get FCK backcheck, which FC means attempt to execute non-executable memory. So let's just see if it all works. This is again my VM, and this is the kernel debugger which debugs it. The exploit executes so many times by now, but of course the physics on the stage like changing. So I really hope that it will work. If not, there is a video from WSL, so you can see it there. But let's hope that everything will be fine. So let's go to the POC. Thank you for telling me that. Okay, good, thank you. You caught me in the right exact moment. Okay, so let's execute the POC. Of course, here we have the kernel debugger, and so that's the VM. I can see that I mmap the user space address C000, which means that I have a user space address which length C000. I shape the page pool, I trigger the C pages, like manage the sham, just like I told you, and then I trigger the corruption. And now you can see that the system will halt. Great. You can see the FC backcheck, but I want the WinDebug to tell it itself. So attempt execute of non-execute memory. Fantastic. Everything works just like we expected. And the address that the kernel jumped to is D200, which is a valid user space address. And I want you to see the flow. Come on. The flow is from sham et syscall to VFS file map, which is the virtual function I just described, and to D200. Everything works great. And now the only target that I need to solve is to disable SMAP. That's it. Okay, so let's go back to the slides. And we can finally solve the last problem. Okay, so we need to disable SMAP, right? We have time. Yeah, we have time. So I need to disable SMAP. And in order to do that, I need drop, right? No, that's a very massive lie. No, I don't need drop. I need the ability to call a chain of kernel functions. That's it. I don't need to corrupt the stack. I don't need to reference the RSP to the page pool. I don't need to do that. I just need the ability to call a chain of kernel functions. That's it. And actually, I get that for free, right? Because how I trigger that jump? I just fake some structure which sits in user space, and I trigger the sham at syscall on it, right? Okay, fantastic. But if I just find some pivot which will disable SMAP, I can set that address at the sham structure, issue the sham at syscall, jump to it, and then change the content of the structure at user space, because it remains at user space. And then I can replace that content and set there another address of the shellcode, for instance, and then issue the sham at syscall again. So actually, I have here the ability to call a chain of kernel addresses as many as I like. And that's power that you can get when you don't do very, very shitty tricks and you work hard to gain strong primitives, okay? When I have kernel object at user space, I basically own the system. I can do whatever I want. So yeah, I am about to do the exact steps of just issue the sham at syscall in order to call pivot, which will disable SMAP, replace the content, set there the shellcode address, which sits in user space again, so I don't need to gain allocation on the page pool, which I can control the content and know the address. I just jump to shellcode at user space, okay? Fantastic. The only problem is that, of course, I don't know addresses. And if I want pivot, which disables SMAP, it has to be valid code in signed drivers, and I don't know the addresses of the page pool, the non-page pool, the drivers, or basically anything, because there is a KSLR overall. So I need to break KSLR. Now, I don't want to gain only arbitrary read primitives, because it won't be enough after the Kratos updates. So Microsoft randomized the HAL heap, which of course was a very, very sad moment to all of us. But if I gain both a relative and arbitrary read primitives, I can break the KSLR. Now, there will be a lot of people which again tell you, okay, dude, great, let's shape again, let's trigger the vulnerability again, and let's find some fucking other structure, corrupt it. No, we don't do that, okay? Shape again and trigger the vulnerability again will affect the reliability of my exploits. And I work so hard so far to gain something really, really stable, so I won't, in any manner, I won't operate the vulnerability twice. I don't do that, okay? People should trigger wild copies on the page pool twice, okay? And moreover, I have another demand. I want to gain those read primitives from the very same sham object I just corrupted. And I can do that easily. I can do that by just note that in addition to the sham at syscall, I have the sham control syscall. And the sham control syscall has command of IPC stat. And IPC stat is just command that tells the kernel, hey, dude, I want you to give me info about that sham ID. So, of course, the kernel won't give you pointers, right? It just writes to you the sham ID, some integers, and some metadata. But I corrupted some sham structure on the page pool. So if I issue sham control syscall with IPC stats and with the sham ID of the sham object that I corrupted, I will gain that pointer from the header. Now, I told you I want to dereference that pointer, but I can read it. And that pointer points to address on the page pool. Paged out address, yes, but I know that from some offset, an exact offset from that address, I have my structure, my sham structures on the page pool. So I can do that trick in order to break the KSLR of the page pool. Now I know where on the page pool my objects are sitting, and if I gain arbitrary read, I'm done. Because I can use arbitrary read in order to read those absolute address on the page pool and break the KSLR. And this is a really, really cute trick I attached to that one. It came to me in a dream, and it's a very funny story, but it's extremely simple, okay? You have a chain of sham object at user space. All the sham object has the next pointer. I can get the sham object linked list back to arbitrary kernel address, and if I just know uint16, okay, just short value that sits there, which will be the sham ID of that sham structure, I can arbitrarily read it. And I can trigger it as many times as I want, because again, this last sham structure sits at user space. And here you can see, I hope that you can see, if no, again, the slides are on my GitHub, that I break in order the page pool, the file object, the LXcore base address, and since I didn't find a pivot which touched the CR4 like register, and I need to change the CR4 because the 20 bit in the CR4 is the bit that indicates map, I didn't find pivots in the LXcore driver which touch the CR4, which makes sense. I break from it the base address of NTOS. And in NTOS kernel, of course, I have many gadgets which touch the CR4. Now, if you want to see the pivot is extremely trivial, I found function in the NTOS kernel which do move CR4, RCX, and retain. And it's extremely important that the function won't touch the RSP because I need to save the state of the stack. Because if I won't save the state of the stack, I will crash after the shamet syscall, and I need to maintain the system in like order to call twice. Okay, so I found a pivot which like don't touch the stack. It was extremely easy because it's the NTOS kernel and it touched the CR4 a lot. Okay, fantastic. And now we can continue. So basically, we know what we need to do, right? Like we are done. We shape the page pool, we stop the wild copy, we corrupt the sham structure. From that sham structure, we break all the KSLR of the system. And from that, I can call pivot, which disables map, and then jump to shellcode. Now, I really hope that you note that I didn't gain, and it's really cool part, I didn't gain arbitrary or like relative right primitives. I didn't have to. And it's really cute because I exploit so many vulnerabilities. I don't remember one that I didn't like gain arbitrary rights. And here I didn't have to because I make myself kernel objects at user space addresses. And it's very strong one. This is the POC, but of course we need a final demo. Now, there will be a lot of people which by now like told me, dude, you don't have to execute the exploit twice. But I like really want to, just for fun. So again, this is the VM. Let's hope that it will work. This is the kernel debugger, okay? We can just execute bash. Okay, and we can execute some CMD. Who am I? I am a Marsa, okay? And I need to be anti-authority system. Now I wrote a little shellcode which find the e-process of some structure by just looking for the PID and replace its token with the system ones. Again, it doesn't matter what code you execute, just for the demo, you know. So let's find the PID of the process. We are 5700, okay. Yeah, 5700, yes. So let's execute again the exact POC you just saw 5 minutes ago. A map of the C000 address. Shape the page pool, see pages, like manage the sham. Trigger the corruption, stop the wild copy, sham structure. Now we should see the break of the KSLR. Fantastic, okay? Page pool, file object, LXcore, and NTOS. You can see that the system is live and anti-authority system. Thank you. Thank you. Okay, fantastic. So, Dave Weston. Great dude. I really like that guy. He actually was at Blue Hat, and I talked to him. And Dave, if you see this video, I like really love you, man. Okay. Dave tweets all the time about new mitigation of Microsoft and like really cool stuff. And yes, from Redstone 4, if you have compatible hardware, and you all do because you all have VTX and stuff, you will have VSM enabled by default. VSM will break that exploit because we have the extended page table and we have the MBEC, which won't let me disable SMAP. We have the mode-based execution control. Now, I really want to, I don't know even how to say that. Those team from Microsoft of the Hyper-V and the VSM are terrific guys. Seriously, this was amazing work. Every time I see new mitigation, I like bypass it quite easily. This one is extremely hard. It's in kind of consider like an open problem, okay? We need vulnerability in Hyper-V or in the secure kernel in order to break it, or that you have some secret that I will really be glad to hear. A lot of people like around the world talk about a VSM. It's really, really hard, guys, okay? I don't know how to pass it right now, unless I will have a vulnerability or guest host in Hyper-V or in the secure kernel. Now, I do have an idea how I can escalate privilege of some arbitrary user space process even with VSM, and it's actually quite trivial. I can do the iOS style. I can do a very massive rope chain, which will corrupt the token of the process of some arbitrary user space process, and then I'm done. Now, of course, if you have VSM, you have CFG enable, okay? We have CFG at the user space for 3 years now, but at the kernel space, it was just preparation for that. We don't have actually CFG in ring 0 if you don't have VSM. With VSM, you do have CFG. So you need to bypass CFG as well, and what you can do is just take the whitelist of the function and find subflows of that functions, and when you control the registers, you can create a massive long rope chain, which will do that. You can do that. Theoretically, I didn't do that until the end. I didn't have power to or time, but you can do that if you would like. Of course, that option is not valid. It's not relevant to RCEs or to attack like over USB or something. It's just relevant to PEs, like this one. This is time for shoutouts. I'm grateful for the great guys from the MSRC and the MSFT, Corey, Nate, Matt Miller, great dudes. There are more, of course. I don't remember all of the names. They were really responsive. I talked to them until now about new issues. They are great. Thank you. For Matt Greber for helping editing my terrible English. Thanks. The Blue Hat IL team, and of course for Tomer for the whiskey. You can see the slides and the POC at my repo, okay? It's there. There is the video from the Blue Hat IL and the guys from Recon. I'm sure that there will be video as well, so you can see it there. Thanks for the Recon executive process. I'm really glad that there is a Recon in Europe, so we don't have to travel so far. So again, thank you. You can follow me at the Twitter if you want to see tweets about Hyper-V, kernel exploitation and stuff. And the really strong message that I want to transfer here is that when you exploit vulnerability, don't settle up on very weak primitives, okay? You can work harder and then gain a really stronger primitive which will make your life way easier in the near future. So please do that. If there are questions, I think that I can take them now, and thank you for the listening. Thank you so much.
Questions? Oh.
Thank you for the great talk. I have a question. I'm not sure I really understood when you stop the wild copy using fork and overwriting the argv. Isn't there a copy on write when you fork and you modify memory? Why do you have a side effect on the other process?
Okay. So the address of the argv, which I give to the execv syscall, is just address at user space, right? And the point of the execv is just to read that array of strings. Now, I created this chunk with map shared, okay? So the flag of the map shared is shared between all the user space processes, which are the sons of the main one, which points to the exact same chunk. So, okay.
Any more questions? I think that's everyone.
Okay, thank you.